Hi, welcome to my channel, Jabber Time. This is a very interesting topic. Double integrals in polar coordinates. You need all the skills in polar coordinates for all the coming sections. It's part of the game. Spherical, cylindrical, and triple integration coming. And all of them, you're going to be sometimes forced to use polar form. What do I mean by that? You're going to see some graphs and some examples. So let's get into it. The double integrals in polar coordinates comes from the connection in this graph. This triangle, right triangle, has an x and y. To reach up to this point, you could call it rectangular form x, comma, y. In polar form, you're going to go that much, it's called r, and you go from the positive x-axis theta degrees or radians, and now this point is located at a length of r and away from the x-axis by an angle called theta. Different languages, but they represent the same point. Alright, as you can see, I'm using red and green to highlight things and point to things, and that's my way of presenting and focusing. The main thing that you need to know between those two languages, if you sometimes need to translate between rectangular xy to polar r theta, that's a good connection. To find r, x squared plus y squared is r squared. So you could write r equals square root. To find x, you could just go r cosine theta. To find y, you go r sine theta. We know this from trig. The adjacent is r cosine and the opposite is r sine. I covered that in detail why in previous videos. But let's move on. The regions R in polar coordinates in general, they go this way, r theta, not xy, where r varies from 2, from a length to another length. It doesn't have to be always from 0. And the theta goes from an angle to another angle, alright, alpha and beta. Here's an example to show you more about what do I mean by this. You see this region R? It's like I have two circles right here, but they're not graphed fully. The first circle is x squared plus y squared equals 1. And the bigger circle is x squared plus y squared equals 4, a radius of 2 and a radius of 1. If I need the top portion between the two circles, or semicircles, I need to rephrase that as region R, written this way, but take a look at the colors right here. R varies from 1 to 2, including 1 and 2. The equal sign is valid. And theta goes from 0 to pi, not to 2 pi. If 2 pi is going to go like a donut all the way, from 0 to pi. So we're done. At least it helps. You know, with the rectangular form, leaving it x and y, it's kind of hard to integrate here, because the lower graph is a square root of 1 minus x squared, and the top graph, the upper graph, is square root of 2 minus, or square root of 4 minus x squared, right? And putting those on the integration is not easy as using 1 and 2 and theta and 0. That's why polar form becomes so handy when it comes to graphs that are not normal the way we see it in xy coordinates. So when we have a general graph and you want to partition it to give you the concepts, here's how it looks like. So we're going around, and r1 and r2, r equals a, r equals b, theta equals alpha, theta equals beta. So those are my samples, or sample area is going to look like this. It's not going to look like dA back in delta x and delta y. It's not like a small box or square. So r ranges from a to b, and theta ranges from alpha to beta. Well, with Riemann sum, we partitioned that to the delta x, delta A ij, if you remember. In this case, we're going to partition it this way. This is my region, sample region, Rij. This is Ri minus 1. This is Ri. And this is theta j minus 1. And this is theta j. So going from this point to this point, that is theta j minus 1. Going all the way to cover this point, that's theta j. So the difference will give me this angle. And the difference in r will give me this much. And that's the difference in theta. And that's the difference in r. Now, here's the graph in general. We don't want to keep looking at the graph and point to things, but let's just move on and write some notes. The center of this region, Rij, will be r and theta. You reach r halfway, and you reach theta halfway. So it's going to be r between that has the coordinates, this point right there in the center, as they call it, will be this r plus this r divided by 2. That's called average between R2 and R1, if you call it R2 and R1 for the convenience. Same thing for theta. If you have, let's say, 60 and 50, like the first one is 50 and the second one is 60, the average will be 50 plus 60 over 2, which is 55. So we get that. We compute the area of Rij using the fact that the area of a sector of a circle with radius r and central theta, angle theta, is half r squared theta. Now this is not our topic in this calculus, but it doesn't hurt to take like 2 minutes and show you where this comes from. Let me show it to you and I'll come back. Maybe maximum 2 minutes. Here we go. This is the whole area. This is a sector. That's what they call it, a sector. Our graph is not a sector, it's a part of a sector. The area is missing. I call it x. To set up your proportions, this is a smart way to do it. You always could build your own proportions any way you want, like degrees to radians and so on. Under the area title for the circle, it's pi r squared. Under the area for the sector, it's unknown, x. Under the angle for the circle, it's 2 pi, or 360 degree. Under the angle for the sector, it's called theta, right there. Change this to proportions. As simple as that. See, I'm writing the whole thing with fractions and equal sign. What do you do next? Cross multiply. Multiply this, multiply this. That's what I get. Solve for x. Divide both sides by 2 pi. Pi cancels. Pull the 2 out as a half. And now you have it. So the area for the sector of a circle of radius r and theta is half r squared theta. Let's go back to the problem. Back to the problem. Subtracting, let's say you have a sector here all the way down, and you have another sector here all the way down. So subtracting the bigger sector minus the inner sector, I'll get this right here. And that's exactly what this talks about. So I'm going to take half r I squared, the outside r, minus half r I minus 1 squared, delta theta, the inner one. If that makes sense. Doing some algebra, we're going to move on. I'll go a little bit fast because you don't need the steps here. You need the final answer. The final answer is what you need to take with you from now on. Here we go. Let's take a look. So, taking half as a common factor from the left, taking delta theta j from the right as a common factor, I end up inside with ri squared minus ri minus 1 square, which is called difference between two squares. This is how we factor it, like a plus b times a minus b. But look how I'm going to rearrange this. Take a look. I'm going to put this with the 2. I'm going to put this in blue. This is called average. That's Ri star, the one that they were talking about, the center in between. This is delta Ri, the difference. It's called delta. And this is already delta. So in short, the samples delta Aij, those samples in rectangular is called delta x, delta y. In polar, it's right here. To speed up the process and apply the limit and use d instead of delta, now you have it. So in polar form, you want to keep in mind that dA equals r dr d theta. In rectangular, it's dx dy. So now we have one more letter, the r. So I went a little bit fast here because I'm not going to ask students how to derive that. But I think it's worth knowing and believing in it. So this is what you need to take with you from now on. In polar form, you replace dA, which is known as dx dy, by r dr d theta in polar form. Okay, let's move on. Change in polar coordinates in double integral. If f is continuous on polar rectangle, they call it polar rectangle, and it could be like kind of like the graphs we saw, but it's still called polar, where r goes from a to b, but a has to be greater than or equal to 0. Can't be negative, of course, because r is a radius or a length. And theta goes from alpha to beta, where beta minus alpha should be between 0 and 2 pi, including 0 and 2 pi, of course. You can't go like 4 pi and 7 pi to cover the whole thing. You go around one time only without repeating. This is what you need also to take with you. dA is in red, replaced with r dr d theta. So I use colors to distinguish, guys, to make things stand out. And hopefully that's one reason I like to keep going with my videos, because they are more visuals of dry text, let's say. They are with colors and visuals or pictures to show you more. So let's talk about this. Look, x in green, you replace it with r cosine theta. Y in blue, you replace it with r sine theta. And you always replace dA with r dr d theta. Things that you need to know for polar coordinates and polar form. They are on the side. I could skip them, but it doesn't hurt to take like a minute or two and show you. Here we go. The arc length. For the circle, it's 2 pi r. For a sector, it's x missing. I'm going to show you same idea, proportions, how to do it. Arc length for the circle is 2 pi r. Arc length for the sector is unknown. I called it x. Angle for the circle is 2 pi. Angle for the sector is theta. Write the proportion. Cross multiply. Solve for x, divide by 2 pi. 2 pi cancels. So this arc length is r theta. It depends how far you stretch. The bigger the circle, of course, the bigger the length opposite to theta. And of course, the bigger the theta is also the bigger the arc length. So now you have it. And this is called the arc length for a sector with radius r and angle theta is r theta. Here's another thing that you need to keep with you as notes. The sine square formula, the cosine square formula, the cosine 2 theta, double angle, and sine 2 theta. I'm not going to read them, but you could pause the video and copy them down if you want, or come back to it. I'll put it on the timestamps in the description below, in case if you want to come back and use them. Okay, next. Here's an example. Double integral, evaluate. They're not saying volume, they just want to practice. So the function is 3x plus 4y to the second, and we have dA, where r is the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Well, we know this. We saw this before. So we are between 1 and 4 as radius, and we are above the x-axis. So it's this graph. Now we know our limitations. R goes from 1 to 2, 1 to 2, and theta goes from 0 to pi, not to pi. This is a mistake, by the way. It's pi, not 2 pi. So it's kind of hard to take it back now, but just keep in mind, from 0 to pi. Let's move on. I'm using colors, as you could see. Blue, it's kind of hard to see it's blue, but I have x and I have y squared and I have dA. This is my x, r cosine. I like usually to fit the problem on one page if I can, and most of the time I can. One reason why I kind of minimize the font right here, because I want to make it fit. I prefer, to see the whole picture at the end. Because imagine if I work and I keep skipping slides, then at the end you kind of forget what was the graph about, or what was the limitations, or what. So if I could fit everything from the beginning till the end in one slide, that's usually my plan. So here we go. X is r cosine, y is r sine. We have the square. dA, r, dr, d theta. One more time. Just keep this in mind. Square sine and square r, as you can see. Now I'm using red for theta and d theta. I'm using green for dr and r's. We have r square here. We have another r here. That gave me r cubed. We have an r here, but this one gets distributed, so it's r to the second. Once you set the limits, you see I fixed it right here. It's pi right there. You see with the colors, everything is clear. The inside part speaks r1, r2, dr. Once you finish that, you apply the outer one, which is d theta from theta equals 0 to theta equals pi. Working inside, with respect to r, this will act like a constant to me, which is not too hard to integrate. R to the third over 3, 3 cancels. R to the fourth over 4, 4 cancels. And those stay. Plug in 2 for r's, plug in 1, simple math. I get 7 cosine plus 15 sine square. Now I'm speaking d theta, no more r's. We know how to integrate this. We need to replace that with one of the formulas. Now everything same color, except d theta and 0 to pi. Replace sine square with what we know, 1 minus cosine 2 theta over 2. Let's break this down to 2 pieces. And after that, I'm gonna have to integrate. And the integration of cosine 2 theta using u substitution, you need a 2 outside. To balance it, you need another 2 down. That makes this 4, as you could see. 15 over 2 with respect to theta will give you 15 over 2 theta. 7 cosine is 7 sine from 0 to pi. Take your time and get 15 pi over 2. Okay? As you can see, I'm trying to make it fit. And you have all the steps, as you can see. If you need more detail about, if I feel like I'm going too fast, you could pause the video by hitting the space bar, go through it, and move on back again. Find the volume of the solid bounded by the plane z equals 0, which is the xy plane, and the paraboloid z equals 1 minus x squared minus y squared. So it's like a parabola, 3-dimension, shifted up 1 unit, opening down. To explain more, here's a graph. The xy plane down here, the darker color, is z equals 0. That's this one here. This one, the upside down paraboloid, is what I just mentioned. If you take it and write x squared minus y squared inside parentheses and replace it with r squared, I get z equals 1 minus r squared. I'm trying to speed up the process and think polar instead of rectangular, if you notice. Now, the lower one is z equals 0. The upper one is this right here. That's what I have, the lower z and the upper z. Setting them equal to each other to see where they intersect, which is, looks like it's a circle because it's the same opening towards x and y, so it's kind of circular, right? Setting them equal to each other, I get this equal to this. Rearranging, I get x squared plus y squared equals 1. But what is that? That is a circle with radius 1. It's right there. Okay? Now, in rectangular form, that region D down there, they call it D, sometimes they call it R. If I use type 1, type 2 integration, this is going to be my upper curve, and this is going to be my lower curve. But look at these functions. They're kind of hard to use them as y1 and y2. So we're going to think polar. This is my volume. This is my upper function minus z sitting on the floor. Just like in calculus 1 when you integrate, if you have a function and you are integrating sitting on top of the x-axis, you don't go y2 minus y1, you just go f of x. And this is my graph here, which is actually f of xy. That's my upper graph. dA, that will give me volume. I did not write d here because I'm just trying to translate. We agree on this as 1 minus r squared from here. Don't forget dA is rd theta. Now with colors and limits. Multiply r, don't forget this r, always gets inside. R minus r cubed, dr in green, from 0 to 1. From 0 to 1. 0 to 1. It goes from 0 to 1, and that is the circle. Inside it's a disk, so r changes from 0 to 1. D theta on the outside goes from 0 to 2 pi, why 2 pi? Because you're going all the way around. Okay? After that, it's just like simple, regular integrations. So once you understand the problem and understand how to translate to polar form and set up this is the main key. After that, I could go faster. But this is what I take my time to color and highlight and point to. Imagine if you do a problem like this one, but you switch these and you put here 1 and you put here 0 and you put pi here, and that's kind of hard to understand and follow. This has to speak clearly about the problem. The problem is this. If you have completely something different all over the place, after that, I mean, you're wasting time calculating, but the point is, this is critical. And sometimes we ask students to build integration and leave it, not finish, because we want to see this. This is the main part. Okay, let's keep going now. We know how to integrate with respect to r. I keep it in green. Plug in 1 and 0, which is not too hard. Get 1/4. With respect to theta, 1/4 theta, plug in the numbers, and now you have it. Okay, let's move on. In general, it's not gonna be smooth like between circles like sectors. So if this is a curve and this is a curve, that's gonna be my lower, that's gonna be my upper. Look at the arrow right here. This is when we talk about type 1, type 2 from previous sections. So it's gonna be pretty much the same. Theta is gonna go from alpha to beta, but R is gonna not go from A to B, it's gonna go from a function of theta to a function of theta. And this is in general. So it's not always constants here and constants here. This would be a function of theta. Then you use that when you plug in thetas, you'll be ready to integrate with respect to theta. So that's the only difference. But that is a general formula compared to the first one. So expect that sometimes you have functions here. Here's a good example. Because I need all the steps to display to you, I'm trying to make it fit and I don't want them to be close to each other, and that's why I have it. So I'm gonna make everything in detail and fill the whole slide. Take a look. Find the volume of the solid that lies under the paraboloid z equals x squared plus y squared, which is like a parabola 3-dimension, opens up with the vertex at the origin. And symmetric from both ways, from all sides. Like how wide it opens with the x is the same width with the y. Above the xy plane, okay, that's good to visualize. And inside the cylinder. So under this paraboloid, under, inside the cylinder. Let me show you what do I mean. This is a paraboloid, under it, inside this cylinder. Now why the cylinder is graphed this way, I'll show you more details. Z equals x squared plus y squared, that's 3-dimension paraboloid. This cylinder is x squared plus y squared equals 2x. Let me give you more details. I have z equals x squared plus y squared, that's this one here. I could write this as polar z equals r squared. The cylinder x squared plus y squared plus equals 2x. They call it cylinder. Let's see why. To graph it, I'm going to complete the square. So I'm going to rearrange. See, I'm not taking it step by step because I want to save you some time. Rearrange, put the x's to the left. Look at this right here, add 1 to both sides to balance it. And now you have it. How do you graph this? Well, it looks like it's a circle shifted to the right 1 unit, but the y did not shift with a radius of 1. That's a graph. Shifted to the right 1 unit with a radius of still 1, but the y did not shift. Okay. So that's the base of the cylinder. If in 3-dimension, it's going to go up with the z and down with the z. Now, let's find r. A common mistake for this problem, students might think that r goes from 0 to 2, which is not true. Let's find r. I have x squared plus y squared equals 2x. That means r squared equals 2 times r cosine theta. That means r equals, dividing both sides by r, 2 cosine theta. That's your r. R is not 2. So r ranges from 0 to 2 cosine theta. If you are thinking from 0 to 2, this is what you are thinking of. This is when r changes from 0 to 2. But that's not my graph. My graph reaches this way, and reaches this way, and reaches this way, reaches to this curve. And this curve is described to be 2 cosine theta. Something that I'm trying to emphasize that you need to pay attention to and be careful. Everybody should be clear with r changes from 0 to 2 cosine, not to 2. This is from 0 to 2. That's not our problem. Okay. So here's my limitations. By going all the cases, covering all of them, I could tell that theta goes from negative pi over 2 to pi over 2. We're not going from 0 to pi. We're not going from 0 to 2 pi. So from down here to here, negative pi over 2 to pi over 2. So that should be clear from now on, which is critical. I mean, like, if you don't have that clear or good, the problem is going to be wrong. I mean, like, the integration is not going to be right. So that is important. And let's move on. So this is my region D. Down here, it's r theta, where r goes from 0 to 2 cosine theta, and theta goes from negative pi over 2 to pi over 2. My volume is, they say the volume is the double integral of my region right here. So that's my upper and that's my lower. My upper one is this z. My lower one is just the xy plane. This is my upper, so I don't have to go z2 minus z1 dA. Don't forget dA is rd theta, and this gets replaced with r squared right there. That's my limitations for r. That's my limits for theta. I know it's kind of small, but everything is clear with colors. Now let's finish it. R squared times r is r cubed. Let's do the green one. We'll come back to the problem because I don't want to keep writing this in my way. Just work inside. I think we agree on this step. And that's how it works. Now you have x to the power 4, cosine to the power 4. 16 and 4 simplifies to 4. How do you handle this, cosine to the 4? Usually cosine to the second we can, but cosine to the 4, okay, let me help you. Cosine to the second is 1 plus cosine 2 theta over 2. Square both sides, I get cosine to the 4. Well, what's interesting about this problem, instead of replacing cosine to the 4 here, I could just cross multiply. So 4 times cosine to the 4 is this much. And that is what I have for cosine to the 4. So I'm going to take this right here. We know how to do this. We just multiply using FOIL method, distributive, whatever you want. And that's what I have inside. Or what I have. Now, cosine to the second. Cosine to the second is right there. So I'm going to replace it with this. Right there. This is an angle, this is twice. This is the angle 2 theta, this is 4 theta twice. Break it down. This is a half, 1 over 2 half, and 1. That's 3 over 2, 1.5. Just simple algebra. Now let's go back to the problem. The problem was involving the red portion right here. And this is what was inside. I don't have to keep it green. We know how to integrate this. It's not too hard. We use substitution here. U equals 2 theta. We use substitution here. U equals 4 theta. Plug in negative pi over 2 and pi over 2. Take your time. And the answer is 3 over 2 pi. That should do it. I'm doing my best not to go over and make it like lengthy video, but I have all the details as you could see. Hopefully that was helpful. It's about 35 minutes. And I think that should do it for polar form. But keep in mind, polar form is very important for all the coming sections. So you need to master polar form. Probably you need more examples, but I can't make the video like 2 hours. In the meantime, I think that should do it. Thank you very much, and I'll see you in the next one. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.